Hello everyone. So in the last module we had taken up hydraulic rough pipe. So if we just see, if we recall, for the hydraulically smooth pipe we have found, for hydraulically smooth pipe I have 1 by root f equal to 2 log of Re root f minus 0.8. This is what we derived, and we call this as Prandtl's universal law of friction. Prandtl's universal law of friction. Okay, so then what did we do is, then let's go to the slides. If we go to the slides, we compared this Prandtl's equation data with the Blasius equation experimental data, that is F equal to 0.3164 Re to the power of minus 1 by 4. This was Blasius equation. So if I compare this Blasius results with the Prandtl's results, they were reasonably matching, and the match is very good till 1 lakh, and after that the Blasius equation deviates. And these are the contributions by Prandtl, Blasius and Nicoradze. Nicoradze had painstakingly conducted these measurements and given F by measuring the pressure drop. So then we solved a simple problem, so wherein which we tried to get the feel of the Y plus. We just took a 2-inch pipe with a length of 10 meter length. That length only represents that it is a fully developed flow. I have not used the length anywhere in this problem. Reynolds is 1 lakh, viscosity and density of water I have taken. So if I calculate U average, it's 2 meters per second. For water, 2 meters per second is quite a high velocity, and using Prandtl's friction factor relation, you get F equal to 0.018. Taking U tau equal to tau wall by rho, you get 0.09487 meters per second. So F equal to 4 CF, you get tau wall equal to 9 pascals. So by substituting half rho U average squared, you get tau wall equal to 9 pascals. If you substitute Y plus equal to Y U tau by nu equal to, that is 5 equal to Y into U tau, you have gotten 9 pascals, that is tau wall by rho, 9 by 1000 upon nu is 0.001 by 1000, you get 5.27 into 10 to the power of minus 5 meters, 0.0527 mm, which is very small. So it is very easy. The point is, it's very easy to break the viscous sublayer by just making the surface rough. So we said that U average by U center line equal to 2n squared by n plus 1 into 2n plus 1. I am going to derive this in this module. So using this, we got the U center line as 2.45 meters per second. We calculated using the power law, U by U center line equal to 1 minus R by R to the power of 1 by n. We calculated du by dr. So from this, we got du by dr equal to minus ucl by nr into 1 minus r by r to the power of 1 minus n by n. So you get du by dy equal to 25.36 pascals. So if you multiply with viscosity, you are going to get that as 0.02536 pascals, which is very, very small. So if you compare that at the location halfway through from the wall, so 12.5 by 225, because it is varying linearly into 9, if I get 4.5 pascals. So tau turbulent upon tau laminar is nearly 180 times. So laminar shear stress is very, very minuscule compared to the turbulent shear stress. So that's the reason when we derived friction factor relation, we did not take laminar shear stress, we just took A log Y plus B. Now we went for hydraulically rough pipe. What is hydraulically rough pipe? We have defined that pipe in which Y plus is, if the surface roughness epsilon plus epsilon U tau by nu is less than 5, then it is called hydraulically smooth pipe. And if epsilon plus, that is epsilon U tau by nu, is greater than 5, then it is called hydraulically rough pipe, where epsilon where epsilon is surface roughness. So I would like to go back to slides. In the slides, if you can just see that, you just see here, this is my velocity profile and this is the viscous sublayer. If that viscous sublayer, if I zoom in, so this is the rough wall and this is a smooth wall. You see here, epsilon is greater than, in this case, epsilon plus is greater than 5, the surface roughness, the left hand side figure, the epsilon plus is greater than 5, so that's why it is called hydraulically rough pipe. But if you see the smooth wall, so that is epsilon hydraulically smooth wall, the epsilon plus is less than 5, so it is hydraulically smooth. But geometrically, if you see, both are rough, but the one is hydraulically rough because epsilon plus is greater than 5, this is hydraulically smooth because epsilon plus is less than 5. Another important thing is here for rough pipe, F is function of not just Re but also epsilon by D. So then what did we do is we derived u plus equal to 1 by kappa log of yu plus c, nu plus c5 we took, and we said that at y tending to epsilon, u is tending to 0, this is not r, this is y tending to epsilon, for y tending to epsilon, u tends to 0. That gives me c5 equal to minus 1 by kappa log of epsilon u tau by nu. So if I substitute that, I get u by u tau 1 by kappa log of y by epsilon, but I am going to add a constant to compare with the empirical relation. So if I compare with the empirical relation which is available in the literature, so I get actually u plus equal to 2.44 log of y by epsilon plus 8.5. So this is A equal to 2.44 and C equal to 8.5. So then let us run through these steps. So what did we do is we took pi r squared u average equal to integral of 0 to 2 pi r u r dr. So then I rearranged this, changed the limits to y instead of r, so transformed this into y, so I get u dy, so 0 to r because minus has gone, so limits get changed. I multiply by 1 by u tau both sides. On the right hand side I get u plus. So for this u plus I can substitute a log of y by epsilon plus c. So I substituted that, integrated and went through all the steps in the previous module, and I ended up with u average by u tau equal to a log r by epsilon minus 3a by 2 plus c, and substituting a equal to 2.44 and c equal to 8.5 and realizing that u average by u tau equal to square root of 8 by f, I get square root of 8 by f equal to 2.44 log of r by epsilon plus 4.84. So this, if I divide throughout by root 8, I get 1 by, that's where we had stopped, 1 by root f equal to 1.98637 log of r by epsilon plus 1.7112. This is what we had gotten. Now what will I do is I will just write this as 1 by root f equal to 1.98637. I want to write this as d by epsilon, that is I have multiplied and divided it by 2. If I divided it by 2, I have to add 1.98637 log of half. Numerator 2 is 2 into r has become d plus 1.7112. So I get 1 by root f equal to minus 1.98637 because I am flipping epsilon to the numerator. So epsilon by d, numerator denominator I have flipped, that's why this negative sign, plus whole of this, if I take this constant I get 1.1132. Now just let's keep it, and I want this in a particular form, so I am going to change this. So 1.1132 is equal to, I can write this as minus 1.98637 log x if I want to find x. So implies log x equal to 1.1132 upon minus 1.98637. So that is minus 0.56046. So x equal to 10 to the power of minus 0.56046, that fetches me 0.27513, but I want 1 by x, so I get 3.6346. Why did I do all of this? Because I wanted to subsume this 1.1132 into this epsilon by d. So I get 1 by root f equal to minus 1.98637 log of epsilon by d upon 3.6346. So again, Prandtl compared this and found that you can fine tune this constant 1 by root f equal to minus 2 log epsilon by d upon 3.7. You see here, this is actually, it was not Prandtl, sorry, this is von Karman's relation. But what is the interesting thing which is coming out here from this equation is that f is not a function of Reynolds number. It is only a function of surface roughness. So once the surface is rough and the flow is turbulent, remember we are all studying, all of this is only for turbulent flow, my boundary layer is turbulent. So it is only dependent on epsilon by d. Okay, so if we just combine, but Colebrook combines both smooth and rough, so for pedagogic reason let me do that. That is for smooth pipe, 1 by root f equal to 2 log re root f minus 0.8. This is for smooth pipe, and for rough pipe we have just found 1 by root f equal to minus 2 log of epsilon by d upon 3.7. So if we rearrange this for smooth pipe thing, 1 by root f, the same way I did for, I can subsume this 0.8 inside. If I do that, 2 log minus 2 log, I take minus 2 log because I will push this re root f in the denominator, re root f, I can write this as 2.5. The same way I did earlier, you can just do that algebra. So you get this, and combining these two, Colebrook combines and gives one Colebrook relation, 1 by root f equal to minus 2 log of, you now understand why I took minus 2, because there is here minus 2. So I just want to combine log of epsilon by d upon 3.7 plus 2.5 upon re root f. He just combined, there is no maths involved, it's just combined. So this is what is called Colebrook's friction factor correlation. Colebrook's friction factor correlation. So this is something which has stood the test of time, and with all the experimental data this matches. So this correlation is very much used, but this is an implicit equation. As you can notice, this is an implicit equation, that is f is there in both the LHS and RHS. It is little difficult, so it's convenient to use. If it is a rough pipe, it's just convenient to use von Karman's relation. The values are not very different for a given Reynolds number, so one can conveniently use von Karman's correlation for rough pipes. Now if we come to the slides, so equivalent roughness for new pipes, if you really see, for a riveted steel pipe, it's between 0.9 to 9 mm, concrete 0.3 to 3 mm, wood stave 0.18 to 0.9 mm, cast iron 0.26 mm, that is the pipe which you purchase from the market. Galvanized iron pipe 0.15, commercial steel and wrought iron 0.045, drawn tubing 0.0015, plastic and glass, it's going to be 0. It's really hydraulically smooth pipe. So now let me just, one thing which is left out is the empirical power law distribution. Empirical for turbulent flow. That is small little thing which I need to cover. So, I will just complete that now. Empirical power law velocity distribution. So, using pitot tube, experiments were conducted to measure the velocity profile, and they found that the velocity profile follows u by u maximum in a pipe. That is, u by, it will be maximum at the center line, u center line is equal to 1 minus of r by r to the power of 1 by n. So, if I just take again the pipe, and this is my r coordinate and this is my y coordinate. So, I get r equal to r minus y, this is my capital R, radius of the pipe. So, dr equal to minus dy, this we have been doing. So, if I write that, I get r minus r by r to the power of 1 by n, that is y by r to the power of 1 by n. This is what is called, this is experimentally found, and n is a function of Reynolds number, but actually it is a function of epsilon by d also. If the surface roughness is there, it depends on epsilon by d also, but generally we ignore that and take n as a function of Reynolds number alone. So, u upon u center line is equal to y by r to the power of 1 by n. So, now if I want to get the u average upon u center line is equal to integral of u dA upon area u c. U average is nothing but integral u dA upon area. So, u c I have just kept it like that because I want that ratio. So, now let me just focus on integral u dA. So, if I just, we will come back to this equation a little later on and substitute whatever we get about u dA into this equation. Let us call this equation as 1. So, integral u dA is equal to 2 pi integral of u r dr 0 to r. This is taking elemental ring at a radius r, thickness dr, and your pipe radius is r. So, you have 2 pi, r can be replaced by u into r minus y minus dy, and the limits being r to 0. So, 2 pi 0 to r u of r minus y dy. Okay. Now, I will substitute for u as ucl into y by r to the power of 1 by n. So, integral u dA equal to 2 pi integral of 0 to r u center line into y by r to the power of 1 by n r minus y dy. Now, this is equal to 2 pi u center line I can pull out, and r to the power of 1 by n also I can pull out. So, I get 0 to r ry to the power of ry to the power of 1 by n minus of y into y to the power of 1 by n dy. This is what I get. So, now continuing this, integral of u dA equal to 2 pi u center line upon r to the power of 1 by n integral of 0 to r to the r into y to the power of 1 by n minus y to the power of 1 plus 1 by n, that is n plus 1 by n dy. Now, 2 pi ucl upon r to the power of 1 by n, if I integrate this, r y to the power of n plus 1 by n upon n plus 1 by n, that is 1 plus 1 by n I have written like that, minus of y n plus 1 by n plus 1 upon n plus 1 by n plus 1 within the limits 0 to r. If I substitute this, you get 2 pi u center line upon r to the power of 1 by n r into r to the power of n plus 1 by n upon n plus 1 by n minus r to the power of n plus 1 by n plus 1 would be n plus 1 by n plus n by n, that is 2n plus 1 by n. Okay, so r to the power of 2n plus 1 by n upon 2n plus 1 by n. So then again you have 1 plus 1, this also will turn out to be 2 pi u center line. This is also r to the power of 2n plus 1, so I can take out r to the power of 2n plus 1 by n upon r to the power of 1 by n into 1 upon n plus 1 by n minus 1 upon 2n plus 1 by n. So that is 2 pi UCL r to the power of 2n plus 1 by n upon r to the power of n, that is n by n plus 1 minus n by 2n plus 1. So if I take out n common, so that is integral UdA is equal to 2 pi UCL r to the power of 2n plus 1 by n upon r to the power of 1 by n. N if I take out common, 2n plus 1 minus n minus 1 upon n plus 1 into 2n plus 1. So plus 1 gets cancelled out, 2n minus n is n, n into n is n squared, here 2 is there, so I can write this as pi UCL, what is that I get here, 2n plus 1 by n minus 1 by n, that is nothing but 2n plus 1 minus 1 upon n. So you just get it as 2, that is r squared into 2n squared upon n plus 1 into 2n plus 1. If you recollect, we wanted a ratio, that ratio was this, that was equation number 1, u average by u center line, integral UdA by AUC, that's what I wanted. So if I substitute that there, that is u average upon u center line equal to integral of UdA upon AUC, that is integral UdA is what I have found, pi UCL r squared into 2n squared upon n plus 1 into 2n plus 1 upon area is pi r squared into UCL. So you get u average by UCL equal to 2n squared upon n plus 1 into 2n plus 1. This is what I had used in the previous problem. I had said that I will derive it, so we have derived it. It's just an integration, but I did not skip any step just for the sake of doing it. Now if you see this graph in the PPT, if you come back to PPT and see this, so if this is the plot r by r versus u bar versus u center line. If you see this plot, you see this is the laminar one, which is parabolic, and as n is increasing, 6, 8, 10, my profile is becoming fuller and fuller, and u average by u center line is what we had derived. If you see this n as a function of Reynolds number in the next slide, n is increasing with the increase of the Reynolds number. That is what it makes it fuller and fuller. Okay, so with the increase in the n, my velocity profile is becoming fuller and fuller. So you have u average by u center line as 2n squared by n plus 1 into 2n plus 1. So this is what we got. So if we just recollect the whole of this turbulence fundamentals, let's just quickly recollect whole of the turbulence fundamentals. If we recollect, what did we do is we just took up the Reynolds averaging. If we just take up this Reynolds averaging, if you just take the slides, we took the conservation equations and introduced the Reynolds averaging by decomposing the flow into mean flow and the fluctuating component, and defined u bar and figured out that u prime bar equal to 0, and we defined turbulence intensity as u prime squared bar upon u bar. So we did the Reynolds averaging using these rules for incompressible flows, and we found that when we did that, we found that there are additional stresses which are coming, which are called turbulent stresses, and these are the additional stresses which are coming into picture. So these additional stresses are normal stresses and the turbulent shear stresses. So these shear stresses are called Reynolds stresses, and they are, although we have put as negative, they are going to be positive, because negative u prime results in positive v prime and positive u prime results in negative v prime. So tau can be deemed as tau laminar plus tau turbulent, that is mu del u by del y minus rho u prime v prime. And we studied universal velocity profile, where we said that 3 layers are there: viscous sublayer where laminar shear stress dominates, outer layer where turbulent shear stress dominates, and in the overlap layer both are equally important. So we gave the universal velocity profile using this universal, and we did the same Reynolds shear stress averaging for the energy equation also, and we found that there is a closure problem, and we defined the eddy diffusivity in terms of the mean velocity. Why this quest? Because always we want to express things which are measured with respect to pitot tube. So we have done that, and there is still a closure problem. We did the universal velocity profile in terms of u plus and figured out that we derived u plus equal to y plus for laminar sublayer and u plus equal to a log y plus plus b for turbulent boundary layer, and found this a and b from the experiments. That's why this is semi-empirical. The relation, the form of the equation comes from fundamentals, but the constants come from the experiments. That's why it is called semi-empirical relation, that is law of the wall. You can extend this to the 3-layer model, and Prandtl's mixing length hypothesis gives us the epsilon m relation in terms of kappa and y and del u by del y. And then we went to friction factor, and we derived the friction factor using this universal velocity profile as given here. So you can just see here that the friction factor is 1 by root f 2 log of Re root f minus 0.8. Similar exercise we did for hydraulically rough pipe, and we got that as minus 2 log of epsilon by d by 3.7. So combining this, we got the Colebrook relation. So you have the, and also the velocity profile, you found that average by center line is given by a relation. So much about the turbulence fundamentals and getting the integral value from the universal velocity profile, the friction factor. One can actually do for temperature also, universal temperature profile, and derive Nusselt number also. If time permits, we will do that. Okay, thank you.